Okay, we can start in 1 minute. At firstly, I would like to introduce Dr. Danny Horta. Dr. Danny Horta is a Mary Skłodowska Curie Research Fellow at the Institute for Astronomy at the University of Edinburgh. Previously, he was a Flatiron Research Fellow at the Center for Computational Astrophysics in New York. He obtained his PhD from Liverpool John Moores University. His research focuses on the analysis and modeling of peak survey data of Milky Way stars, with a particular emphasis on spectroscopic data. Today, Dr. Danny Horta will present his talk titled "A Glimpse into the Milky Way's Distant Past: High Redshift Galaxy Formation with One Galaxy." We warmly welcome him.
Thank you, Furkan. Can everybody hear me okay?
Yes.
Excellent. Yes, thank you very much, Furkan, for this invitation, and to everybody here for attending. Apologies I can't be there in person, something popped up. But nonetheless, I'm excited to be able to share some of the work that I work on, looking at how we can learn about galaxy formation in the early universe using our own galaxy, the Milky Way. So as Furkan just said, my name is Danny Horta, and I'm a postdoc at the University of Edinburgh. So okay, let's get started. So yeah, as the title says, this talk will focus on trying to answer two pivotal questions using the same data. On the one hand, I want to try and give you an overview of what we've learned about how we think the Milky Way is assembled over time in the early universe, in the first few billion years of the universe. And at the same time, I'm going to use those inferences and observations to try and constrain galaxy formation in the high redshift regime using our own galaxy. So before I delve into all that, how do we think galaxies form and evolve? Well, in large measure, in our current cosmological paradigm, lambda CDM, we think the galaxies grow in this great measure via this mass assembly history. So it's a hierarchical mass assembly history, whereby small clumps in the early universe coalesce with each other, small halos, and the stars and the galaxies within them merge and get accreted onto larger mass systems, and as time goes on, these systems grow in size over time. To illustrate my point, here's a video from the Fire cosmological simulations showing you how what will become something like the Milky Way evolves from the early universe until present day. And you can see how these small building blocks, as I call them, merge together and merge onto larger mass systems, and as time goes on, this galaxy grows in size over time. Now, if you're someone like me that aims to try and reconstruct or understand how this galaxy formed and evolved, and this key formation mechanism of galaxies, what you'd attempt to do is look at the properties of stars in the stellar halos of galaxies. And this is because the stellar halos are the galactic component that retain the stars and the material from these different accretion episodes. And therefore, the chemical, dynamical, and age properties of stars in the stellar halos of galaxies retain the fossilized clues or the imprints that we need to then understand and examine to reconstruct that assembly history process. And here I'm showing you an example with simulations on the left of what stellar halos look like, and you can see there are clear stream features and overdensities, what we call shells. And on the right, I'm showing you the biggest picture we have so far of the Milky Way stellar halo, where you can see how there's been a flurry of different identified objects, both in stellar streams, like Sagittarius stellar stream, or dwarf galaxies and debris, and so on. Now, if you're aiming to do this this sort of work in galaxies outside of our own, so outside of the Milky Way, this becomes very tricky. So it's very good because you get a full view of the galaxy, allowing you to probe into the really distant regions of the stellar halo. Like, for example, if we looked at Andromeda, our closest disk galaxy neighbor, you can see that we can really probe the outer regions of the stellar halo. But it's very difficult to obtain really detailed measurements of individual stars in this region. As well as this, we can't really probe the central regions of the stellar halo where most of the material is, and where we really need to try and understand stellar populations to really disentangle the accretion process that led to the buildup of this galaxy. Another example is for example, Centaurus A. where you can identify prominent features from recent accretions, but you can't really disentangle the properties of stars in the inner stellar halo. Now, because we sit within the Milky Way, we have this unfair advantage that we can probe our galaxy in a level of detail that we cannot do with any other system in the universe. And this is because we can study the detailed properties of individual stars for now large samples, on the order of millions and billions of stars. And this has really led us to piece together in fine-grained detail the stellar halo of our Milky Way. So in the 90s, we discovered that there is this currently accreting dwarf spheroidal galaxy, which we call the Sagittarius dwarf spheroidal. So this is a system that's currently accreting onto the Milky Way as we speak. Even earlier than that, millennia ago, earlier tribes and civilizations knew that there are two satellite galaxies in the Milky Way's halo, the Large and Small Magellanic Clouds, which are currently infalling into the Milky Way as we speak. These, of course, due to the interaction, will be accreted by the Milky Way and will be destroyed and will later form part of the Milky Way stellar halo. However, with the advent of Gaia and large-scale stellar surveys, there's been a flurry of streams identified in the stellar halo as well, which are the result of this accretion process or the dissolution of globular clusters. And thanks to the really precise measurements that we're getting of stars in the stellar halo, we can now identify groups of stars that might not be coherently together right now, but they share common properties in the form of chemical abundances or integrals of motion and the orbits of their stars that we can link together. And these are the debris from earlier accreted systems. And the poster child discovery for this was the Gaia-Enceladus sausage accretion event, which was identified with Gaia DR2 in 2018. However, this picture that we now have of the Milky Way and this really detailed view wasn't always the case. If we go back to the earliest maps of the galaxy that we ever created, the view that we had was like this. So in the 1700s, William Herschel and his sister put together this catalogue of, I think, binary stars, which was the first documented catalogue of the night sky in the Milky Way. And here what he did was he took painstaking observations of the night sky and then by hand made measurements of stellar objects in the night sky. Of course, in this map, there are systems that are outside of the Milky Way as well, but the majority of points belong to stars in the Milky Way. Now, since then, we've come a long way, and the not so far or not so old picture of the galaxy is like this, and this was largely thanks to the Hipparcos survey, which was the first to measure for large samples of stars near the solar neighborhood, detailed positions and velocities of stars in the form of astrometry, allowing us to understand the kinematic properties of the nearby galaxy or near the solar neighborhood. And in addition to that, there was also works trying to obtain detailed stellar spectra from which you can determine individual element abundances, allowing us to probe also the chemical DNA of the galaxy and the stars. But now, thanks to the advent of large-scale stellar surveys and particularly the Gaia space satellite, we have this view of the galaxy, which is just unprecedented. So because of this survey and all these surveys coming online, we're currently living in a new era for galactic astronomy, which is the era of large-scale stellar surveys, which are just providing us with a colossal amount of information. And particularly for Gaia, as shown in this image, it's delivering detailed astrometric solutions, so positions and motions of stars in the night sky, as well as it will deliver spectroscopy for millions and billions of stars. So we're talking large data sets. Now, complementary to Gaia, there's also been a flurry of spectroscopic surveys that have aimed to complement early versions of Gaia by adding detailed spectroscopic observations. And one of the ones that I'll talk about a lot today is the Apache Point Observatory Galactic Evolution Experiment, and I'll tell you why in a second. So when you combine all these data, you see the galaxy in over 30 dimensions. As I mentioned before, the astrometry, when combined with the line of sight velocities from spectra, allows you to have 60 phase space information that allows you to compute the kinematics of stars, so the velocities, as well as you can integrate orbits in a given potential to determine orbital parameters, orbital energies, actions, etc. The detailed spectra allows you to figure out things like the conditions of the star, so the temperature, the densities, and the luminosities, but they also allow you to figure out the detailed element abundance ratios, so the chemical DNA of stars. We're now, for a large sample of stars, also determining ages in many different ways, either by isochrone-based ages or by using element abundance ratios and so on. And of course, Gaia is also providing an amazing amount of photometry in the form of magnitudes and colors, allowing us to construct these beautiful CMDs, or color magnitude diagrams. Now, all this data comes in three main flavors. You have detailed spectroscopy, which, as I mentioned before, gives you stellar parameters, the chemical DNA of stars in the form of element abundances, and of course the line of sight velocities, which when combined with the astrometry, the positions and the proper motions and distances, allow you to determine kinematics and orbits of stars. So together, this gives you a chemical dynamical data set. In addition to this, you have photometry, so how bright a star shines in a given wavelength regime, which gives you a magnitude, and if you take the difference between two of those, that gives you a color, allowing you to construct beautiful color magnitude diagrams, which are extremely informative in their own way, but allow you to also determine things like stellar ages and so on. And then all combined, this gives you a really vast and rich data set, which, as I mentioned before, you cannot get for any other galaxy in the universe, right? This level of detail is paramount. So for this talk, I'm going to particularly focus on a data set which uses a combination of the Apache Point Observatory Galactic Evolution Experiment, or Apogee for short, with Gaia. And the advantages of using this survey is that, firstly, it's a near-infrared spectroscopic survey, and because it observes in the longer wavelengths in the near-infrared, it can pierce through the dust and gas in the midplane much easier, allowing you to probe the central regions of the galaxy and the disk in a level of detail that wasn't being able to do so before. But in addition to that, it's a dual hemisphere survey, meaning that it observes both in the northern and southern hemisphere, allowing you to capture the full sky. An Apogee has now finished, but it delivered an incredible amount of data. So the latest data release delivered 1 million spectra for about 750,000 stars, from which, again, element abundances, stellar parameters, and line of sight velocities were delivered. And the key thing about Apogee is that it delivered really precise element abundance measurements for up to 15 different elemental species, spanning nucleosynthetic channels, so the alpha elements, ion peak elements, odd Z, and even some S process elements. Now, if you combine that information with the astrometry from Gaia, you get this really complete chemical, kinematic, or orbital data set for about 750,000 stars. Now, for large samples of these stars, we also have detailed age measurements as well through Zeta-N age measurements in red giant stars. All this data set, in addition to all the work from Gaia, has been revolutionary for trying to figure out the accretion history of the galaxy. And with all this data, there's been a flurry of discoveries of phase mixed debris, so stars in the stellar halo that don't appear to be together, but share a common orbital and chemical origin, which we then can trace to different accretion events. And each of these accretion events has been given a fancy name. So as I mentioned before, we've known Sagittarius and the LMC and the SMC for a while, but in 2018 with the Gaia DR2, there was this discovery of the Gaia Enceladus or Gaia sausage accretion event, which is the remnant of a major, or what we think is a major accretion event in the Milky Way's life, approximately 8 to 10 billion years ago, and of similar mass to the LMC. In addition to that, there's been a bunch of smaller mass debris like the Sequoia or the Thamnos or Helmi stream and so on, and as well as many stellar streams which have been identified. But the one that I'll be talking more about today is the one that our group identified, which is called Heracles. And different to all the others identified substructures, which were primarily identified in the outer regions of the stellar halo, Heracles was identified in the heart of the galaxy, in the central regions of the stellar halo. And I'll tell you why that's interesting in a second. So with all this data and all these discoveries, we've been trying to piece together the assembly history of our own Milky Way, both to understand how our galaxy formed and evolved, and to understand if it's typical amongst other disk galaxies in the universe. And in order to do that, people have either focused on looking at the recent assembly history, so things that have happened more recently, like the infall of Sagittarius and the LMC, and how this impacts the evolution of the galaxy, but also how it perturbs dynamically the Milky Way system. And this has been particularly interesting in recent studies that aim to try and understand how the LMC is perturbing the Milky Way potential and how we can then look at that to understand how the galaxy is formed and is evolving. But I am particularly interested in looking at the earliest phases of assembly history. And this is for several reasons. The first is that the early building blocks are the most massive ones in terms of mass ratios. And these constitute the bulk of the stellar halo mass, especially in the inner regions of the stellar halo. In addition to that, these early building blocks supply the necessary baryonic material, gas and stars, that allow the formation and the fueling of the genesis of disks, including our own Milky Way disk. Therefore, they dictate key episodes in the formation of galaxies. So I'm really interested in trying to understand how many building blocks it took to form the Milky Way, what their properties were, and how they led to the formation, and what impact they had on the formation of the galaxy, which all fall into understanding galaxy formation at high redshift. Now, in difference to work that is looking with JWST to the early universe, as shown here, this is really interesting and amazing work, of course. We're probing the most distant regions of the universe and the early stages of the Big Bang. However, the level of detail that we get for these systems is, while unprecedented, is this, right? We're getting blobs in an image. Now, another thing that's very uncertain with these sort of measurements is really pinning down the redshift at which these systems are. So you can find blobs, but really understanding at what redshift you are observing them is something that is highly debated in the literature. However, in the Milky Way, because we can observe stars on an individual basis and really probe their properties in a level of detail that we cannot do with extragalactic observations, if we mine stars in our own galaxy belonging to these early building blocks, we'll be able to obtain a level of detail that's not even afforded with JWST. And this is the sort of game that I play. I'm trying to find these systems to understand their properties and understand their build-up in the galaxy. However, I'm not the only person doing this. There's been, with the advent of Gaia and other surveys, different works attempting to do this. So, for example, Hans Walter Rix with the Gaia data found this poral heart of the Milky Way, this spheroidal population in the central regions of the galaxy that appears to be somewhat centrally concentrated. We found this building block that I'll talk to you about in a second called Heracles, again buried in the central regions of the galaxy. And together with the student, as well as other works, we've been trying to also understand the spin-up of the disk and how the disk went from a very chaotic and proto-galaxy phase into a very coherent and kinematically structured population. However, for now, I'll talk to you about how we went about discovering this, what we think is a major building block of the galaxy. So as I mentioned before, this was done with a combination of apogee and Gaia data, so chemical and kinematic or orbital data sets. And previously, compared to previous results and previous studies, what this study really showed was that the synergy between these two data modalities is really advantageous to identify different building blocks. And the reason why is the following. If you use particular element abundance ratios, for example, this one shown here, so on the y-axis, I'm showing you the ratios of stars and particularly the magnesium to manganese ratio. So this is a type 2 core collapse supernova tracer with magnesium, and manganese is a type 1a supernova tracer, so white dwarf binaries, probing different nucleosynthetic origins. And then on the x-axis, I'm showing you the aluminium to iron ratio. And for reasons I'll explain in a second, if you plot the Milky Way data, you can see that it congregates in three main loci. You have this top left region, which I call the unevolved region, or what people call the accreted region. You have the in situ region, which is divided into two blobs. You have the high alpha in situ region and the low alpha in situ region. And actually these correspond to the alpha bimodality that we observe in the Milky Way's disk. Now, the reason why this region is called the unevolved or accreted region is because galaxies and stars in galaxies chemically evolve in this manner. You start off in the top left, that region of the diagram. There's higher amounts of core collapse supernovae. Type 1a supernovae which have a delayed onset, haven't begun exploding yet, and therefore don't contribute much manganese. Aluminium is depleted in metal poor populations, so earlier chemically enriched populations. So therefore you start in this region. Now, if you were the Milky Way, you would follow this red trajectory, and with increasing core collapse supernovae, you would go like this, and then when the onset of type 1a supernovae start to kick in, you would spin down like this. However, if you're in a accreted dwarf galaxy, the time you spend in this region, because you're evolving slower compared to larger mass systems like the Milky Way, is longer, and therefore if a system accretes onto the Milky Way, its star formation quenches, and therefore it will remain fossilized in chemical space. What this means is that while the Milky Way is chemically evolving and will evolve out of this region, systems that accrete onto the Milky Way, because it takes longer for them to get out of this region, will appear fossilized in this diagram, in this region of the diagram. And when you look at Milky Way stars at present day, this means that this region of the diagram will be dominated by accreted populations. So therefore, if you take this aluminium selection, and then you select these stars and compare their orbits against stars that are deemed chemically in situ, you find the following. So here I'm showing you a plane that people use a lot, which is the orbital energy as a function of angular momentum. So stars that are less bound have higher energies. Stars that are more bound, centrally concentrated in the Milky Way's potential, are low energies. And then things that spin with the disk in a prograde fashion have a positive angular momentum, and things that are rotating against the Milky Way's disk have a negative angular momentum. And this leads to this sort of triangle shape. Now, if you take the chemically unevolved or chemically accreted stars and plot their distribution, you see this image on the bottom, where you have two clear overdensities, one at high energy and one at lower energy, for roughly zero angular momentum, separated by this energy gap. However, in the top panel, if you plot the metal poor in situ populations, you find that there's a much smoother distribution, leading to like a trajectory like this, and then some heated populations, which these are the result of the splash, the merger of the Guy-Enceladus sausage heating disk populations. So then what you find is, in the accreted population, there are two clear overdensities, right? The one at high energy corresponds to the Guy-Enceladus sausage, and the one at low energy corresponds to this identified population, which we deem is Heracles. And the reason why we deemed it as Heracles is because not only is it distinct in chemical abundance and orbit space, if you model the chemical abundances across different regions of the diagram for centrally concentrated stars, so stars in the inner galaxy, shown here on the left, and you model this using a Gaussian mixture model, you find that the model, the best fitting model, finds an overdensity of stars here in the metal poor regime, which corresponds to this Heracles accreted population. So the model suggests that there's an additional population there. Now, if you then check theoretical expectations from cosmological simulations, and particularly look at Milky Way mass halos in the Eagle simulations, you find that about a third of these galaxies have a centrally concentrated early building block, which appear to have the same chemistry and the same orbits as what we find for the Milky Way and Heracles. Interestingly, you can then take, because we have all these elements from apogee, you can then take them and do a statistical comparison to compare how similar the chemical abundances are between that and other populations, like, for example, the Guy-Enceladus sausage, as shown here. So in this later work, we develop a new statistical method that aims to statistically quantify how similar or distinct different populations are. And here I'm just showing an example comparing Guy-Enceladus to Heracles and how these are statistically distinct when compared at fixed metallicity. So in summary, from this work, we found this new population in the heart of the galaxy, which we think is the remnant of a major building block of the Milky Way. And given its initial properties, we suggested it amounted to a significant fraction of the total stellar halo mass, but only a very small fraction of the mass within this inner 4 to 5 kpc region. What's interesting is that people looking at globular clusters have also found that there's an overdensity of globular clusters that share the same chemical and orbital characteristics as Heracles, which do not follow that of globular clusters which we think formed in situ in the Milky Way. And this is what you would expect for relatively massive systems, that were accreted, they should have some globular clusters as well. So I think this is supportive evidence that there is a building block in the heart of the galaxy. So building on from this work, we aim to assess and model the mass of this system to try and understand how much mass it actually comprises and when was it really formed. So in order to do that, we used a statistical technique that aims to model the density of stars using a Poisson point process, taking into account the apogee selection function, the different density forms that we used, and dust maps and extinction. And what we aimed to do was to test a variety of different models, ranging from simple power laws all the way to complicated triaxial, twisted, broken power laws, etc. And what we do is we fit using a Bayesian likelihood method with Markov chain Monte Carlo procedure, the best fitting model. And then when we have the best fitting model, we integrate its mass to weigh how much mass this system comprises. So what we did was we took the sample from apogee, and then we employed this chemical selection to select unevolved stars. And then when looking at their orbits, so the apocenter radius, so the most distant point in their orbit, you see that there are two clear peaks here. One corresponds to the Gaia-Enceladus sausage, as I showed before, but this inner peak corresponds to Heracles and populations comprising the protogalaxy. So in order to then do this in a way that it's unbiased and without spatially selecting stars in the inner galaxy, what we did was we took the unevolved stars and then plotted the magnesium to iron as a function of iron over hydrogen distribution. And this is what you see here. The parent sample shown as a 2D histogram in the background, where you can see the alpha bimodality in the Milky Way's disk. And then if you plot the unevolved stars and color it by the apocenter radius, you can see that the track at high alpha corresponds to stars concentrated in the inner galaxy, i.e. Heracles and the protogalaxy. And then the track in following the yellow trajectory corresponds to the Gaia-Enceladus sausage. So what you can do then is you can create a chemical selection of different bins across metallicity and then model each population independently and all the populations together. And this is what we set out to do in this work. So then by fitting a range of different models, we select stars in these chemical cells and then model their density. And we found that the best fitting model across all cells, and when model all cells together, is this triaxial Plummer model, which has a scale radius of about 5 kiloparsecs, which is what we expected given that we found the majority of Hercules stars in the inner regions of the galaxy. And that appears to be flattened, so it appears to be squashed and slightly prolate, sorry. Now, the interesting thing is that when integrating all the mass from all these chemical cells, so the ones shown here, so all this trajectory here, we found that the total mass is around 10 to the 9 solar masses, which is roughly the mass of the stellar halo quoted so far. Now, what's interesting is the Heracles accounts for approximately 2/3 of this. So about 7 times 10 to the 8 solar masses. So that means that Heracles is of similar mass to what the slightly less massive than what the LMC is currently today, which is quite interesting. So we think this system, because it's buried in the heart of the galaxy, deep in the potential well, and it shows these chemical abundances that are alpha enhanced, so it didn't reach the metal-rich regime. We think that it's the debris of a building block that happened very early on in the Milky Way's life, and therefore had its star formation quenched early, and that sunk deep into the potential of the host of the Milky Way. And we found that its mass is still quite significant, so 7 times 10 to the 8 solar masses, which is about 2/3 of the total stellar halo mass estimated to date. So how do you get these systems? Is it normal to get systems like this in Milky Way mass galaxies, or is it just that the Milky Way is atypical? So in order to answer this question, I set out to conduct an experiment looking at cosmological simulations of Milky Way mass galaxies to try and understand 3 questions. What constitutes a proto-Milky Way system? So these early building blocks that come together to set the genesis of the Milky Way. How massive are they? And what are the observable properties? And how do they compare to things that we found in the Milky Way? So if I was to go and mine these things in the galaxy, what properties should I use? So in order to ask these questions, we use the Fire cosmological simulations, which are a suite of 13 Milky Way mass halos, simulated at high resolution. So we're talking on the order of 10 to the 4 solar masses per star particle, and they're in a cosmological setting. And the beauty about Fire is that it has two suites. It has the Latte and the Elvis suite, which uses isolated Milky Way mass halos in the Latte suite, and we have 7 of those. And then you have Elvis, which simulates pairs, like a Milky Way and Andromeda system in this local group environment. So by comparing these two, you can also compare different environment assemblies as well, which is really interesting. So to ask this question, we first needed to set out to identify what constitutes a protogalaxy, and then obviously search for all the different building blocks that form it. So there's many different ways that have been you could do this. We decided to find a time in the evolution of that Milky Way mass halo in which the main branch, as I call it, so if you were to take the simulation at present day and run it back to the beginning, the halo that the simulation says this will become the Milky Way mass galaxy, that's what I'll call the main branch, and everything else I'll call a building block. So the time in which the main branch reaches a 3-to-1 stellar mass ratio with the second most massive system is the time in which we stop and we say, okay, before this time, everything that came together is what we'll call the protogalaxy, and everything else we'll call later mergers. And the reason why we did this is because it's an indication that this system is dominant in its environment. There won't be any really massive mergers happening on after this point. It is very reproducible to be done across simulations. And the beauty is, because we're looking at the observable properties at present day, we aim to understand what they look like in chemistry and kinematic space. By using this selection, we didn't bias it by performing a chemical or kinematic cut. And this then allows us to track each system independently and the star particles belonging to this system, and then separate them to understand each building block independently. So then, in my definition, a protogalaxy is comprised by a main branch and then building blocks that merge onto that main branch before this time in which the system becomes very dominant in its environment. So if you then use this definition and look at Milky Way mass halos in Fire, you find the following. Here is the mass ratio between every system and the total mass in the proto-Milky Way as a function of the stellar mass in each system. And I've shaded the region here where you have the most dominant systems, and this is because they contribute a significant amount of mass to the total proto-Milky Way mass budget. Now, across the different halos, you find that 8 out of 13, so approximately 60 to 65%, formed predominantly by one dominant main branch, meaning that there's only one big clump at the beginning and then smaller mass clumps of much smaller mass. However, for 5 out of those 13 proto-Milky Ways, there is an additional significantly dominant building block that also comprises the majority of the mass in that proto-Milky Way mass system. And I found this really interesting because if Pericles is what we think it is, it's likely to be one of these systems. Now, if you look at how much mass there is in proto-Milky Way systems, it ranges from 10 to the 6 to about 10 to the 10. And this does not vary significantly between isolated or pairs, meaning that environment doesn't play a big role. However, you do find that main branch typically are much more massive compared to building blocks, but there are some building blocks that reach the same mass as the main branch. Now then, what you can do is you can assess how spatially concentrated different systems are depending on their mass. And this is what this plot shows. But it's very complicated, so I'll just summarize by saying that the majority of the mass across all the simulations for the proto-Milky Way is contained within 5 to 10 kpc from the galactic center. However, what's really interesting is that it can extend to beyond 40 kpc. So the regions where you'd expect the stellar halo to be comprised of later mergers or systems formed very later, this region can still inhabit stars that were part of this proto-Milky Way system. Now, what's interesting is that some building blocks, especially the most massive ones, show a similar spatial profile to the main branch, meaning that if you were to try and find these early building blocks based on their spatial position when compared to stars formed in situ and the oldest stars formed in the Milky Way, it'd be very difficult to disentangle them. We then looked at the kinematics, and we aimed to assess how rotationally supported each system is at present day, and how that varies as a function of their shape, and specifically the ellipticity. So on the left, I'm showing you a measurement of kappa, which is how much energy essentially the system has in the plane of the disk at present day. And on the right, I'm showing you the average azimuthal velocity. And you can see that there's no real difference between building blocks and main branches. Then it doesn't matter how big it is or which environment it formed in. They all seem to have some weak but systematic net rotation at present day, which I think was interesting. So it's not zero, there's some small rotation, which may be linked to how then the disk formed out of the galaxy. So, in conclusions, given all this work, we found that the earliest memory history of the Milky Way is crucial to unravel, to understand both its genesis, but to also understand and place constraints on galaxy formation at high redshift. And I think that in addition to the work with JWST, the Milky Way provides additional help to disentangle this in a level of detail that is unafforded by these big telescopes. In the Milky Way specifically, the data suggests that there is a major building block in our galaxy, this Heracles population, and that it's comprised of the central regions of the Milky Way, in the Milky Way's heart, and that amounts to a significant amount of mass when compared to the stellar halo mass. So on the order of 2/3 of the total stellar halo. Now this population seems to be well described by this plumber model, this triaxial plumber model that is flattened in the Z direction, so sort of oblate, which is quite interesting. Now predictions from simulations suggest that things like Heracles can exist, both from Eagle but also from Fire in this more detailed analysis. And they suggest that proto-Milky Way systems form from one or two main components plus a handful of smaller mass systems. And the ratio of this between 1 to 2 main components is roughly 60 to 40%, so it's pretty well distributed. So I think this was really interesting to understand, to then try and piece together how these early building blocks lead to the formation of a galaxy like our own. So given all this work, what's next? How can we push this further? Well, the next phase of the Sloan Digital Sky Survey, SDSS-5, has a Milky Way mapper program that will be looking at this inner region of the galaxy in an even more crazy level of detail. So to show this, here's a face-down projection of the Milky Way and the targets for apogee on the left, and then galactic genesis or Milky Way mapper on the right. And you can see how the numbers will just increase exponentially. So specifically, galactic genesis will deliver between 3.5 and 4 million spectra at a level of resolution similar to apogee, allowing for us to determine individual element abundances for large samples of stars. And specifically for metal poor stars in the inner galaxy, like Heracles, this will jump from Heracles. Currently we have about 500 stars. This will jump to about 70,000 stars. So just an incredible jump in the number of targets that we'll be able to obtain, allowing us to really probe this in a greater level of detail. In addition to SDSS-5, which I am involved in, there will also be Foremost, which will have its formidable survey that aims to obtain high and low resolution spectra for stars in the inner galaxy. And this will be complementary data that will be really advantageous to study, hopefully in synergy with SDSS-5, to try and piece together what Heracles is, what its properties are, and how many more building blocks comprise the inner regions of the stellar halo. Now, similarly, in the form of low resolution spectra, Gaia has and will deliver an incredible amount of data. So currently we have 175 million BPRP, which allows us to get global metallicities and in some cases bulk alphas, but just for an incredible amount of targets. However, the next data release from Gaia, DR4, will also deliver medium resolution optical spectra for about 40 million stars, for which a large number of them will be in the inner regions of the galaxy. So the question doesn't become how will we obtain this data, but how do we synergize and make a catalog that uses all this information together. So to do that, I think we need to develop new data-driven models, both in the form of generative or machine learning models, to process this data and to be able to extract all possible information in the most precise and accurate manner. And to that end, I've been developing a new method called LUX that aims to synergize different spectroscopic data from these different large stellar surveys. So with all this data, I think the next questions that we can start tackling is when and how did the Milky Way's disk emerge? There's been some work involving this. However, I think that we need a lot more data in the inner galaxy to be able to answer this question. And actually, this is something that Furkan and Olcay are thinking of doing. They're trying to understand the properties of the old disk. So that'll be interesting. I think it'll be equally as interesting to answer how many building blocks it took to form the protogalaxy of the Milky Way and what their size were, how this then leads to what we know about bulge formation in the Milky Way. Do we have a pseudo bulge formed by the bar? Do we have a classical bulge? Do we have both? Then asking the question of, is this typical and what environment leads to a sort of galaxy like our own is really interesting, especially when comparing to M31. Which will start to obtain more data and an equal level of data compared to the Milky Way. And then I think that a more distant project or sort of question that we need to answer is what present-day observables of the Milky Way, for example, the chemical disk biomodality, its thick, thin disk transition, its splash stars, etc., was influenced by these early building blocks, and how can we connect this to then the later accretion history of the Milky Way and understand our assembly history in more detail. So with that, I'll go back to my conclusions and I'll say thank you for listening, and if you have any questions, fire away.
Thanks so much for amazing time planning. If you have a question, you can ask. Okay, no question, I guess. No question, right? Okay. I'm just wondering, Darren, and ask one question to you. To be able to observe split stars and the proto Milky Way must have at a certain density mass threshold, I think. And I was wondering what the density or mass of the proto Milky Way might have been after Heracles merger. Can we redefine up split stars, and we are looking to, can we choose it could be part of Heracles or Gaia Enceladus or the other streams, or I'm just wondering that.
Yeah, I think things like this will be able to help. So for example, disentangling different mergers. We know that different mergers, depending on their properties, how fast they form stars and how long they form stars, will lead to different chemical fingerprints. So here's an example showing you two, Heracles and Gaia Enceladus. So you can then use abundances, which should be an unbiased way of selecting stars to then model their spatial density. So you could do things like that. For disentangling building blocks from the proto-Milky Way itself, like the oldest stars formed in situ, this is going to be extremely challenging for the reasons that I list with the results from the simulations. They show a very similar profile, they show very similar chemical signatures, and they show very similar kinematics. When looking at the chemical signatures, we just looked in the simulations at alpha and iron, and this is because it's very difficult to model individual elements in precise detail. However, I think there's new computational ways of handling this, so more simulation results will be able to guide us on how to do this. But I think maybe more exotic elements like heavy R process elements, S process elements, which have more stochastic formation pathways, might be helpful to disentangle building blocks like Heracles from the oldest stars formed in situ, especially at fixed bins in metallicity. You really need to do this in different waves or different regions of metallicity space, because just looking at alpha iron mixes a bunch of things together. You have to use individual elements to be able to disentangle the properties in greater detail.
Thanks so much. If you have more question, thank you so much, Danny. I hope you see you again in Istanbul, in your life with the good days. Have a great day, everyone.
Thank you very much for having me, and everybody attended. Thank you. I'll stop sharing.